Hello, my name is Linda Xu, and I'm a postdoc at the Berkeley Center for Theoretical Physics. This paper, written with collaborators Nick Rod and Ben Safdi, is about the near-future prospects of searching for thermal Higgsino dark matter. The nearly pure Higgsino is one of the best motivated theoretical particle models of dark matter, and the minimal thermal realization precisely predicted at 1.08 TeV has been up to now entirely experimentally unprobed. One of the most promising avenues to finally discover or rule out Higgsino dark matter is to target products of its present-day annihilations into gamma rays, whose spectrum in particular contains a characteristic line feature at the dark matter mass. This work focuses on searching for these gamma rays produced near the Galactic Center, which dominates by far the signal luminosity in our local universe. A number of current and near-future observatories present as very promising candidates to search for the signature. H.E.S.S and Fermi in particular are notable in contrast to the others shown for being in operation and having a substantial amount of data on disk already. Analyses from the H.E.S collaboration have already placed very strong constraints on continuum dark matter annihilation using an on-minus-off subtraction analysis and is well positioned to make discoveries at TeV energies. This would have translated to an up to 4 sigma discovery potential for the Higgsino, depending on the underlying dark matter profile, if the data were reanalyzed using the strategy we recommend. However, we are concerned that H.E.S has overstated their instrumental sensitivity by quite a large factor, roughly 8. While we do not have access to the proprietary detailed instrument responses, the same forward model must relate the different components of on-sky fluxes, misidentified cosmic rays, diffuse emission, and putative dark matter to their respective recorded counts. We find that the strength of their dark matter limits, which we can faithfully reproduce, would imply a suspiciously efficient cosmic ray rejection, and more importantly, a large excess of diffuse emission, which is seen in the same patch of sky by Fermi, which is nonetheless missing from the reported H.E.S data. Shown in purple here is what the diffuse residuals should have been if the emission matches the expectations set by the Fermi observations. And shown in the black error bars are the data actually reported by H.E.S. If we calibrate the instrument response to match the known strength of galactic emission measured by Fermi, we find an effective area reduction of about a factor of 8, which translates to much less optimistic prospects for Higgsino discovery. With the publicly available Fermi data and our best, but admittedly limited and imperfect reconstruction of the corrected proprietary H.E.S data, we perform some of the most sensitive dedicated searches of thermal Higgsino annihilation to date, under a range of dark matter profile assumptions. We find that Fermi data leads in sensitivity, but still falls short by a factor of several in probing the prediction for most of the profiles considered. In a more future-facing direction, we also consider 2 upcoming observatories. CTA, which, like H.E.S., is an imaging air Cherenkov Telescope Array, which promises improvements in effective area, field of view, background rejection, and energy resolution. SWGO, on the other hand, is an extensive air shower array, which trades resolution and background rejection for much more efficient exposure accumulation and larger field of view. We find compelling discovery potential in both, though the details will depend on several factors. One of these factors is the shape and abundance of the underlying dark matter profile, of which we are fundamentally ignorant. To cover a larger range of more realistic possibilities, we consider the dark matter density distributions of a suite of Milky Way-like hydrodynamic simulations from the FIRE project. The dispersions in profile shapes from this collection indicates that the fundamental uncertainty is quite large, though it may be encouraging that one of the most Milky Way-like of these, Romulus, yields also the strongest signal prediction. Another one of these factors of a more controllable nature is the analysis strategy employed. We find that modeling the background components yields substantially better sensitivity than symmetric on-off subtraction methods, especially for the more realistic hydrosimulation profiles, while remaining comparatively robust. This is especially true if we can leverage information about each component's spectral shape in a template, such as taking dedicated off data for the cosmic ray background and by using the Fermi diffuse model for galactic emission. Finally, I'd like to focus in this on this plot in specific of the discovery test statistic for the thermal Higgsino over a range of the considered dark matter profiles. Also shown is the test statistic necessary to make a discovery of a certain amount of sigma. The darker bar in each color corresponds to our benchmark to template analysis, while the lighter bar illustrates what is theoretically possible with perfect background knowledge. For both of these experiments, but especially for CTA, we project quite exciting prospects for significant discoveries over a large range of these profile possibilities.